Welcome, guys. Today we are talking squares, square roots, and the real number system. We're going to jump into just an initiating question that I'd like you guys to take a look at. This is similar, not an exact story from my summer, but pretty close. So Mr. Newbar would like to make a square garden to grow tomatoes. His plans are to have a garden with an area of 100 square feet surrounded by a gravel walking path that is 2 feet wide. He intends to use 4 inches of gravel for the walking path. How many cubic feet should he buy? So I want you guys to take a look at this and think about it a little bit. You can definitely pause the video and attempt to solve this problem on your own if you'd like to. All right, you can definitely pause. But what we're essentially looking for is if we want 4 inches of depth, so 4-inch deep of gravel, that covers all of this area here. Everything here is going to be walking path, all over here. And we've got a 2-foot distance from the edge of the garden to the outer part of the walking path. How much gravel do I need to buy? How much cubic feet of gravel should I buy? And this is actually going to play into the concept of squares and square roots pretty nicely. So pause, think about it if you need to, but I'm going to jump into the solution to this right now. Now, this is our picture, okay? If this is 100 square feet, if the area here is 100 square feet, that means that we need to come up with how wide our garden is going to be. How wide is this garden? If we've got a square with 100 square feet, we need to figure out the lengths. Well, this would be a 10 by 10, right? This is a 10 by 10 garden. All right, 10 times 10, or 10 to the second power, would get us 100 square feet. Now, what I'm thinking I'm going to do in this is I'm going to subtract off the area of the garden from the area of the total. Well, if we've got 2 feet in distance here, and 2 feet in distance here, and 10 feet of distance here, that means that this distance is going to be 14 feet, right? So we've got a 14 by 14 square that's subtracted off by a 10 by 10. So 14 to the second power, subtracted off by 10 to the second power. And what that's going to tell us is it's going to tell us the area of what's left. And it's going to tell us the area of these, or of this gravel here. Now, 14 to the second power is 196, and 10 to the second power is our 100. That's our 100 square feet. When we do this subtraction, we get 96. So we need 96 square feet of gravel. And if you remember back to the beginning question, we wanted that gravel to be 4 inches deep. Okay, 4 inches deep. Well, if I'm asking for cubic feet, 4 inches is approximately 1/3 of a foot. So I would take my 96, which is just the area of this, and to find the volume of it, I would multiply by 1/3. Multiplied by 1/3, and that would give me my answer, 96 minus 1/3, or 1/3 of 96, which is equivalent to 96 divided by 3. Should get me, I think, 32 cubic feet. So I need 32 cubic feet of gravel in order to fill my gravel pit, in order to fill my walking path. And what I wanted to do is start with that problem because it has a lot of different ideas between squares and square roots. Okay, we had to take a square root of 100 to find the number 10, right? We had to take the squares of several numbers, which is the numbers times themselves. And that's our topic of conversation today. Objectives that we have: understand the relationship between square of a number and a number's square root. We want to determine some rational approximations of perfect and non-perfect square numbers, and also understand the difference between rational and irrational numbers. Okay, those are our objectives today. Now, let's start with what we in the math world refer to as the real number system. Okay, all of our numbers in this class that we deal with will be considered real, and believe it or not, there are imaginary numbers that you guys will deal with more in Algebra 2. But basically, the definition in my mind of real is anything that has a position on the number line from negative infinity to positive infinity. Okay, anything along this line. Now, there's a lot of different representations of numbers. There's a lot of different ways you can show numbers, but anything that has a spot is considered real. Now, all real numbers have a place on the number line, and all real numbers are also classified as either rational numbers or irrational based on their characteristics. And the last understanding we have to get towards is that the same number can be shown in a lot of different ways, okay? The number 1, for example, can be shown the standard way. It can be shown like this. It can be shown pi over pi if we wanted it to, okay? But it all is a different version of the number 1, right? Let's talk about a number, okay? 6, okay? Many different ways that we could represent the number 6. 6 can be shown as an improper, 12 over 2. It can be shown as a square root. Square root of 36 is the number 6, which is what we'll talk about a little bit today. There's so many different ways that we can represent just this one location on the number line of 6. All right, so think about that. There's many different versions of the numbers 1, 2, 3, 0. Okay, a lot of different ways that we can show it. So squares and square roots, we're going to start with this. These are opposites of each other. Okay, the square of a number is the number times itself. This is read the number squared. So if I say 3 squared, right, what I'm referring to is that number times itself, 3 times 3, which is 9. Okay, 4 squared is that number times itself, 4 times 4, which is 16. All right, now opposite of squaring a number is taking its square root. You're asking yourself what number times itself gets you the number inside the symbol. Some of these are really easy. Square root of 16 is just the opposite of 4 to the second power. We're asking us what number times itself gets us the number 16. Well, that's easy. That's 4. But the square root of 17 is not so easy, okay? Because there aren't really nice numbers times themselves that get us the number 17. In fact, this square root of 17 is an irrational number, meaning it'll be pretty messy. What we're going to learn today is how we can use the square root of 16 to help us estimate the square root of 17. All right? This is going to be kind of a messy number. All right? Let's jump into some examples here. Squares of numbers, this is something that maybe would be a good idea to just have in your notebook. 1 to the second is not 2, it's just 1. 2 to the second power is 4. 3 to the second is 9. 4 to the second is 16. I'm going to go fast. 5 to the second is 25. 6 to the second is 36. 7 to the second is 49. These are numbers to have memorized. 8 to the second power is 64. 9 to the second is 81. 10 to the second is 100. 11 to the second is 121. 12 to the second power is 144. 13 to the second is 169. 14 to the second power, this is where I get a little bit caught up. This one, I believe, is 196. Okay, I always kind of flip the numbers, 169 and 196. 15 to the second power is 225. And 16 to the second power, 16 to the second power is, I think, if I remember correctly, 286. I might need to test myself on that one. 16 times 16. 256. 256. I knew it ended in a 6. But these are just the squares up to 16. There are plenty of them. If you want to find another one, just take any number times itself. Now, a perfect square is kind of the opposite of what we just came up with. All right, you can come up with perfect square numbers just by taking any number times itself. 144 is a perfect square because 12 times 12 is 144. All right. Knowledge of our perfect squares helps us to estimate the non-perfect ones. So we look at this number line shows square root of 1, which is 1, 2, 3, 4, and so on. 9, 10, and 11, okay? And we have to have these memorized. We have to have these understood because we can see that there's only 3 units of difference between 1 and 4, okay? 4 and 9. But there's a whole bunch of numbers in between 2 and 3 that are considered irrational numbers. You take things like the square root of 5, square root of 6, square root of 7, and so on. Now, perfect squares, as I said, help us to estimate some of the non-perfect ones. What we're going to do is try and estimate square root of 70 to the nearest 10th. Now, as I look back on my list here, I'm going to try and identify what 2 perfect squares the square root of 70 would be in between. And I'm seeing that somewhere in between the square root of 64 and the square root of 81 is where that square root of 70 would lie. Because again, all we're trying to do is estimate it. So we've got square root of 64. And we'll put over here the square root of the next perfect square, which is 81. Understanding that the square root of 64 is 8, and the square root of 81 is 9. So when we're looking for the square root of 70, we know it's lying somewhere in between there, right? Well, it's only a couple units, square root of 70. Let's just estimate it here. I wouldn't say it's all the way, or it's halfway in between 81 and 64, but I'm going to say it's maybe a little bit less than half. 64 and 70 have a difference of 6 units, whereas 70 and 81 have a difference of 11 units. So my estimate for the square root of 70 is going to be in the region of about 8.4, 8.3, 8.4. And you can definitely check those on a calculator by just punching them in and come up with the exact value. But today we're just estimating. We're just trying to get in the ballpark. Let's estimate some others. Square root of 8, you guys can try these on your own. Square root of 28, square root of 133. 8, somewhere in between the perfect squares, square root of 4 and the square root of 9, which would be 2 and 3. So we know that the square root of 8 is somewhere in between these two numbers. My guess would be pretty close to 3. So I'm going to estimate it at 2.8. Again, we can check it on a calculator if you want, but we really just want to have a good understanding or a baseline understanding. B, square root of 28. Well, somewhere in between the perfect squares of 25 and 36. A little bit closer to 25, so my estimate on this is going to be, I don't know, about 5.2. Okay, we're going to estimate it at about 5.2. Square root of 133. Going up the list a little bit, somewhere between 121, which is one of the perfect squares. This would be 11. And then square root of 144, which would be 12. Well, let's see, 133. 33 is about 12 units away from 21. And 33 is about 11 units away from 44. So this is probably smack dab in the middle. We're going to estimate this at 11.5 units. Again, you can punch it into your calculator to check. Square root of 61 should be just a little bit less than the square root of 64. My best estimate here is going to be about 7.8. So again, what we're trying to do is just use the knowledge of perfect squares in order to estimate the ones that are non-perfect. We can also take square roots of fractions, right? We're asking us what number times itself gets you 25 over 36. And hey, look, 25 and 36 are perfect square numbers, right? The way that we would do that is by taking the square root of 25 over the square root of 36, and then just writing our answer down. This would be 5 over 6. 5, 6 times 5, 6 would give us 25/36. For B, square root of 1 over 9. Again, 1's a perfect square, 9's a perfect square. So we would do square root of 1 over the square root of 9, and then simplify the problem. This would be just equivalent to 1 over 3. Now I should make the disclaimer here. Technically, 1/3 is the square root of 1/9, as is negative 1/3, right? So we should put this little symbol in here that says plus or minus. This plus or minus symbol just means that we refer to both roots, the positive and the negative. Unless, and I'll use this one as an example, you see a little negative symbol in front of it, right? If you see a negative symbol in front of the square root, then you're just looking for the negative root, okay? So 12 over 2, neither of those are perfect, so all I'm going to do is simplify what's inside. 12 over 2 is another version of 6. So I'm taking the negative square root of 6, not a perfect square, so now I'm going to look to estimate this value. This is somewhere between 4 and 9, and probably just a little closer to 4. So I'm going to estimate this as negative 2 points, let's just call it 4, negative 2.4. Again, you can check it on a calculator if you need to. Last one here, 16 over 4. If you want to reduce the fraction right away, you can. Well, 16 over 4 is a version of the number 4, and you don't see any positive or negative version of the number over here, so we're going to write plus or minus 4. This is the square root of 4. Oops. Plus or minus the square root of 4, which is a positive or negative 2. I think you've probably seen some things with square roots before, so this is maybe a little bit of review for some, right? Now, those non-perfect squares makes up the largest selection of what are known as irrational numbers. And in order to understand irrational, I think it's important and imperative to understand rational, right? Rational has the word ratio. So a rational number is any number that can be written as the ratio of two numbers. Some examples, fractions, anything that's written like this, a over b, is a rational number because it's written as a ratio of two integer values. Any terminating or repeating decimals because they can easily be converted into fractions. You think of a terminating decimal like 2.4, well, that could be written as 2 4/10, right? It's a fraction. That means it's a rational number. Or even a repeating decimal like 1.3 repeating. 0.3 repeating is a way of representing the fraction 1/3. This is 1 1/3. Anything that's written as a repeating decimal or a fraction, or a repeating decimal or a terminating decimal could be converted into a fraction, right? And then any integer values, anything like 4, because it could be easily converted to 4 over 1. It's a ratio. 5 could be easily converted to 5 over 1. -6 can easily be converted to a ratio, -6 over 1. Right? So as we said before, all real numbers are either rational or irrational. Okay? Rational simply means it can be written as a fraction, a over b. And then there are smaller subsets of rational numbers, right? The next smallest subset of rational numbers would be the integers, right? Which is numbers like -2, -1, 0, 1, 2, and so on in both directions. These are all integer values. We also have whole numbers that kind of make up our subsets, right? Whole numbers are basically anything that starts at 0 and goes forward, right? Basically just positive integers are the whole numbers. There's another subset called natural numbers, but the only difference between natural and whole numbers is the number 0, so I'm just going to leave it out of here for simplicity, okay? Now, another element of rational, if you think of the number square root of 36, okay? Square root of 36 simplifies to a rational number, therefore square root of 36 is rational itself. But the square root of 35 would not be rational because it does not simplify to a rational number. It simplifies to a very messy number. Which brings us over to the irrationals. Again, I kind of call these the messy ones. Messy numbers. One of the most popular irrational number is pi. You guys have probably seen pi a lot in 7th grade, 3.14159. It just never ends, it never terminates. These are all the irrationals. And then any square root of a non-perfect square. Okay, non-perfect squares, examples being square root of 10. You know, there's no integer value times itself that gets us 10. Square root of 28. These are all irrational numbers, and all we can do is estimate them at least right now. There is a way to rationalize them that we'll learn about later, but for now, just have to recognize and say, hey, that's an irrational number. All right, last thing we'll do today is take a look and just classify each number. So the first one, a, -12, that's a negative counting number. This is an integer. All right, it's also rational. Number 2.45, not an integer, but it is rational because it's a terminating decimal, so we're just going to classify it as rational. All right, square root of 10, anytime you see the square root symbol, you're thinking, is that a perfect square? And the number 10 is not. It's not, you know, it's pretty close to the square root of 9, which is equal to 3, but this is an irrational number. Square root of a fourth. If we can simplify it down to something rational, then we know it is rational. Square root of 1 over square root of 4. Well, both of those numbers are perfect square numbers. This is 1 over 2, which is rational. So that's its classification. 3 pi plus 1. If you see pi, you know it's irrational. Even if it's being multiplied, added, subtracted, doesn't matter. An irrational number can't be written as a fraction. And the last one, f, square root of 1 over 2. Well, let's try this. Square root of 1 over the square root of 2. Square root of 1 is easy enough. That's 1. But the square root of 2, that's an irrational number. It's going to get you something messy. So this is irrational. So recap of today, hopefully numbers are starting to kind of clear up a little bit. Numbers with a spot on the number line are considered real. Okay, and as I said at the beginning, there are imaginary numbers, you just won't talk about them in this class. All real numbers are considered rational or irrational. They can be broken down into those two subsets. And then we can make a rational approximation of numbers that are irrational by using our calculators, that's one option, or just using your knowledge of perfect squares. All right, I hope that moving forward, if I gave you a number like this, square root of 11, that you would know, hey, that's an irrational number, but I know that it's pretty close to 3, just a little bit above it, because the square root of 9 is 3. So the square root of 11 is 3 point, let's just approximate that 2, about 3.2. All right, hopefully you guys found the video helpful. Hopefully we have learned something a little bit about squares, square roots, and the number system.